I'm Judy Sandrock, and in this next session, we're going to be covering Earth observation applications using satellites and ground segments. This is part of the SES Space STEM Outreach Program. So what I've done is that I've drawn up an agenda. We're going to go through some welcome and introductions. What is Earth observation? Space to decision chain, satellite communication. We're going to go through 3 African applications, and then there's going to be a discussion and a conclusion. So in terms of welcome to this workshop on Earth observation data, and how we actually apply it using satellite connectivity and analysis on the ground. And I am Judy Sandrock. I run the Space STEM program for BaxIQ Space. One of the projects that we are implementing across the African continent is engaging schools and nonprofit organizations to engage with learners and students, to introduce them to the value of the space economy, not only in their everyday lives, but also as career opportunities going into the future. So what is Earth observation? What we have is, in this graphic, you can see here that what we have is we have a number of different satellites that are in orbit. This is a graphic representation, so they're really not this close to each other, and they probably aren't in exactly the same orbit, but this just gives you an indication of the different types of satellites that there are in orbit. So what we have is we have the satellites orbiting the Earth, and what they're doing is that they're collecting data about our planet. And so when we have a look at the sensors that they have on board, these will be cameras. So they will be collecting, for example, infrared data, multi-spectrum data. They'll probably be looking at images, kind of photographs. So we're going to see some examples of those a little bit later. These sensors capture the images and the measurements that we can't actually see from the ground. So where I'm sitting right now, if I was outdoors, even if I was on a flat plane, I wouldn't be able to see further than 18 kilometers, because technically 18 kilometers is where the horizon is. So I cannot see if there is a flood, a river that's going to burst into flood over the horizon. I cannot see that there's perhaps going to be a drought in an area that's very far away in a wilderness area. And also 70% of our planet is covered by ocean. So what we need to do is we really need to monitor those oceans, because it's absolutely crucial for us in terms of sustaining our atmosphere and sustaining our livelihood. So the data helps us monitor weather and crops and oceans, and as I mentioned, a whole lot more. And information guides us better to make better decisions for communities and governments. So what it is, in order to make any kind of a decision when you're in a position of leadership, whether it's government, private sector, perhaps you're a farmer or you're in a community and you're responsible for people, what it is that you need 2 critical things to make a decision. First of all, you need the knowledge and the experience. And second of all, you need accurate, up-to-date data in order to actually apply that knowledge and experience that you have so that you can make a decision. If you don't have up-to-date and relevant data, then you cannot make decisions, and you actually cannot make sure that everything is great in terms of livelihood and sustainability. So what we refer to is the space to decision chain. So what we have is, as I mentioned, we have our Earth observation satellite that is going to be in a particular orbit. It will have been designed and built with particular sensors on it, and it'll have that particular altitude of orbit, so that what it can do is it can actually take those images and everything will be in focus. For example, if you're wanting high resolution images of what is happening on the planet. And so if this is our target area, then our satellite then is able to take those images. Now, as the satellite orbits the planet, what it'll do is it'll monitor what you can imagine a strip across our planet. So as it's in orbit, it can actually service more than one area along that line. And so that either that information can come directly down to a ground station if it is going over a ground station at that particular time. But sometimes, let's say, for example, it's now over the ocean and there's a 70% likelihood that it's going to be over an ocean, then what it'll do is that there won't be a tracking station that it can relay that data to. So what it'll do is it'll actually send it to a communication satellite that is sitting in a much higher orbit. And so when we went through when we were taken through the structure of SES satellites and the various orbits that they have, when Hans Heldenhuis, the head of Africa, took us through, we noticed that there were these various orbits. So a lot of these communication satellites can be at a higher orbit than an Earth observation satellite. And then what happens is that satellite then relays the data to a receiving station. Also, that receiving station can also actually get that data directly from that Earth observation satellite. So as you can see here, there's multiple options to be able to recover that data that's being collected of that target area. And then what happens is then through a connection to the internet, and probably a number of different servers. There's a processing station. The data is stored in a database. It can be stored in an MQTT database and server. And then that information is processed and it's provided to organizations who perhaps subscribe to that data. Otherwise, what it can be is that it can be made publicly available in some cases, so everybody, the user or the normal person in the streets or in a village, can actually access that information. And I'm going to once again give you some examples of that. So here we refer to this as our space to decision chain, so that everybody can receive that data so that they can make effective decisions. So satellite communication is absolutely crucial to this entire process. Not only do we have the satellites collecting that data, passing over ground stations, but we also have communication satellites that could be collecting that data, but they in turn also need to download to ground stations. So what I'm going to do is that I'm going to go through 3 African applications. And before that, I can see that there's 2 questions in the chat. So if you don't mind, what I'm going to do is I'm now going to just go away quickly and have a look at those, and then I'm going to come back to that. Okay, so Richard Nags is asking, what is a SES satellite? So SES Satellites is a company, and that company is an amalgamation of 2 different organizations. So previously, we had a very strong relationship with Intelsat, and Intelsat managed over 50 satellites in orbit. And then there was they were acquired, and there was a company that was formed called SES Satellite, because Intelsat was acquired by a company called SES, which is a European company. They also manage a number of satellites as well as ground segments, ground stations. So now SES is a much larger organization with much better coverage and a much larger satellite fleet. So let's go back to our 3 African applications. Firstly, the first application we're going to look at is early flood warnings. So here I just have some screenshots and I have some images from the different African nations that have Earth observation data available for their populations. So we can see here, Zimbabwe, they have a look at flood and drought monitoring. There is an Africa-wide Flood and Drought Monitor, which is run by the African Union. The South African National Space Agency also monitors water, rain levels, floods and droughts. And then we have similar in Mozambique, in Namibia, in Malawi, in Morocco, and Madagascar. So what you can see here is that there's a number of governments who are providing data for not only for their farmers, but for their general populations. And all of this data, in many cases, is actually collected by exactly the same satellites. But then what it does is it goes through to the different organizations. They can then interpret it and then pass that on to everybody in their country. So what we have a situation right now where there are sufficient satellites in orbit that can scan Africa every 15 minutes. And those particular satellites can detect rainfall, and they can also detect levels of dryness. So they can, using a multispectral camera, what you can do is you can measure humidity levels. And the reason why you can do that is because the moisture in the air will absorb certain wavelengths of sunlight. So when that multispectral camera passes over that area, what it'll do is because those wavelengths of sunlight are being absorbed by the moisture, therefore that satellite won't be able to detect it as it would in terms of just broad daylight, normal dry air or vacuum daylight. So what it is that the satellites then scan every 15 minutes. They can detect rainfall from cloud cover, and they can also detect humidity. This data feeds into computer models for 6-hourly flood forecasts. So there's a running 6-hour forecast on, are we going to have floods based on rainfall and humidity levels, etc. Authorities can then be alerted, and they can in turn alert their communities before those floods arrived. And so this is used very much in Ethiopia, West Africa, Southern Africa, and of course across the continent. Here we have an image. This is courtesy of the South African National Space Agency. And we can see here that this is an area, this is in KwaZulu-Natal. This is the river, a satellite image that was taken a few days before the flood. And then we can see over here, it's actually the eThekwini municipality, which is previously known as Durban. And I'm going to show you an image of the harbor that they have nearby. And you can see here, the river has burst its banks, and this has actually been the impact. You can see that a number of these areas here have been flooded, and all of this vegetation has been washed away. And that vegetation would have been creating a very nice barrier for these buildings over here. So this actually shows the impact of the damage that was caused. So these images are also very useful when one wants to do disaster recovery, as well as when perhaps some of the homeowners or factory owners are going to be claiming from insurance. Then the insurance companies use these images to actually detect, did that damage happen actually with that flood, and what was the extent of the damage, etc. What they can also do is that they can also start being proactive, and they can actually start anticipating that they're going to get claims from people or from those that they've insured. So the second application we're going to look at is farming and drought planning. So in the previous example, we had a look at how rainfall and drought is also monitored. But now what we can do as well is we can actually look at how do we plan going into the future using this data on an ongoing basis. So what we have, I'll explain this image in a few minutes. So the satellites monitor vegetation health and soil moisture. So here we have a standard image in visible light, what we would refer to as a photograph. And then what we have is here the different wavelengths of light have actually been separated out. So what it is now it's actually looking at the different frequencies of one of the bands. And so what we can see here in terms of the key is this paler white to light yellow gold color is low frequency. And then the darker is a slightly higher frequency of light. And what that is going to give us, and we can actually see here, if we have a look at some of these patches, this dark patch over here corresponds with a very, very green patch here. So what this will do is this will help us to see where is there vegetation, where is the vegetation actually drying out, and where do we actually have areas where it's actually turning into a drought condition. So what also happens is that you can also tell the light images will also give you an indication of what is the temperature on ground in that particular area. What happens with vegetation is that it absorbs sunlight, which interacts with its chlorophyll, and then that chlorophyll converts carbon dioxide into food. And that is, in chemistry, that is known as an endothermic reaction. So what it does is it pulls energy from the environment for that reaction to actually take place. So that is why if you're standing under the shade of a tree, a large tree, it's a lot cooler than standing under the shade, let's say, of a concrete roof, because the thing is that what you have is that the tree is also absorbing energy or absorbing the temperature in the air around it. So when you're closer to vegetation, it's a lot more cool than if you're closer to a lot of man-made structures and buildings. And that's also why if you're in a desert, deserts get incredibly hot because the vegetation has died and there's no cooling effect from the vegetation. So what these images give us is a very good indication of the health of that vegetation. Now, let's say, for example, it may appear dark. It may appear dark because maybe there was a fire. And so we can't actually judge the level of vegetation perhaps from the color, but what we could do is we could judge it from the temperature. So then we know that that area there, it may not look sandy right now to the naked eye, but it actually could. There's a drought possibility in that area. So here, what it is, this is now converted to a map, and then what can happen is that those farmers in that area, or if it's, let's say, a wilderness area, the conservationists can have a look at that and they can say, wow, we need to now start being careful in terms of deforestation and droughts and desertification. So the forecasts help the farmers to plan planting as well as harvesting. And the data will show them which regions face a drought stress going into the future. So application 3 is coastal monitoring. And here is a really good example. Basically, it's people with boats behaving badly. And what it is when we monitor coastlines, this is the Durban Harbour in eThekwini municipality. This is on the east coast of South Africa. And what we can see here is we can see all of these dots over here. And so what it is that the satellite has detected fishing vessels in this coastal water. And what it is that the satellite has detected these fishing vessels, not necessarily because it can see them from a light perspective. What it is that it's picking up electromagnetic signals from those positions. So whenever you have a motor that's running, whenever you have, for example, even a mobile phone running, if somebody's got any kind of device where you've got electricity running through it, then what you're going to have is you're going to have a magnetic current, and then those signals can be picked up by the satellites. very, very, very high sensitivity satellites. And so what it is that the satellites have actually picked up that there are devices out there, probably means that it's ships. Okay. So what it is that this is used to monitor illegal fishing, pollution, and shoreline changes. And the shoreline changes, that would be a fairly similar application to the one where one looks at the flood, the impact of the floods. That would be very much in terms of imagery. And then what happens is that these satellites track ships even when they turn off their identification systems, which is called a transponder. And it's also really great for protecting marine resources and coastal communities. So here I have a comparison. So there's a website, an open website, global website, and what it does is it actually shows the different ships and fishing vessels and boats, whatever size, and these symbols actually relate to their transponders. So what this is actually this is the website where they collect the data, because when they turn their identifier on, their transponder on, it'll say, I am, let's say, whatever, a container ship, and this is my name, and this is where I'm traveling. I'm expected to be in Durban Harbour on this particular day at this time, or whatever it may be. And then there's different types of vessels. So some of them could be Coast Guard, some could be fishing vessels, some could be oil tankers, whatever it may be, cruise liners. And then you can see here that those that are in the harbor already, they have their transponders on, but but the thing is that they're stationary. So you can see that there's only two that are actually moving. The rest are stationary. We can see here's one that's stationary, one stationary, a few here that are stationary, etc. Some are moving in and others are moving out. Now let's compare it to with a satellite image. There's a lot more pings from devices on this satellite image than there is here, where people have actually, they're behaving legally and they've turned their transponder on. So what happens is that this data is then received on the ground in a control room, and then they compare, the team there compares, what are we seeing here, what are we detecting, and who has actually got their transponders on. And so what they can do is they can say, wow, look over here. Okay, we've got this chap over here doesn't appear to have his transponder on. Let's send the Coast Guard out, because this person here is doing something illegal. Either they're fishing illegally, or they're dumping oil, or they are poaching, whatever they may be doing. So this is a really good application where you can see how we can monitor from space, and we can actually really protect all of our coastlines. So at this point, what I'd like to do is I'd like to open it up to everybody so that we can have a discussion, and then we can conclude. So, hi, Richard, I can now see your face. Sorry about that. When I'm sharing my screen and when I'm running the slides, I cannot see everybody. So I was wondering, let me have a look here at the
No
chat. Great. And Richard, you also asking, what kind of sensors do we need to detect submarines, because water can be a challenge? Yeah, Richard, I have to say I don't know much about this. But the thing is that I believe that what one could do is one could have a look for magnetism. The thing is also with submarines is that what they do is that with military submarines, they often want to disguise their footprint. I remember quite a while back when I went for a tour of a magnetic site, calibration site that we have in South Africa. What it is was that if a submarine or a ship or an aeroplane has been sitting in the same position for more than 6 months, what happens is that the iron molecules actually align with magnetic north. And so what happens is, It's really interesting. And so what it does is on the aeroplanes, what that does is that it disrupts the calibration on their compasses and on their navigation system. And then what happens with the submarine is now suddenly it actually gets a magnetic footprint. So what they do is, especially with the submarines, is what they'll do is that they'll actually get these really long copper cables and they'll literally wrap the submarine. And then what they do is that they put a current through it, which then scrambles those molecules, so that what they do is that they're no longer aligned with magnetic north. And so where there's aircraft that are on the ground, if they're going to be on the ground for too long, let's say, for example, they're going through major maintenance and they're going to be grounded for months, what they do is they make sure that once a week they actually change their position so that the molecules don't align.
I remember when we were at Sansa, they have a compass alignment facility there, and they were just talking about making sure that the compasses are calibrated. Otherwise, you have planes and they don't know really where they're going, and every plane has to actually have a analog. Is that the correct term? An analog compass?
Yes.
Yeah.
Just to check. Yeah, absolutely. Yeah. Also, the thing is that we rely very much on GPS style navigation systems. So there's a number of different ones. The European one is Galileo, there's GLONASS, et cetera, et cetera. But what if those systems go down? Also, the thing is that those GPS systems get very badly affected when we have a lot of solar activity, when there's a large solar flare, and our magnetic field gets bombarded with a lot of solar radiation. That really upsets those networks. So yes, planes they need that old-fashioned steampunk looking compass so that they actually can see which way they're pointing. Yeah, cool. Absolutely. So look, I mean, it's a good idea to research how are submarines detected using satellites. Maybe it's actually still an advantage of submarines. You know, they're very expensive and they're really very awful to be in for long periods of time. But maybe in terms of warfare, maybe they're actually still a necessity because they can't be detected unless they're, you know, in shallow water or whatever.
Okay. You had some very, I've seen you speak on similar topics before, and just the topics around mining I found fascinating. And also recently I've tracked some articles on how structures have been found in like the Amazon forest because they're noticing geometric patterns. Could you just elaborate a little bit more on the mining again and how the satellites are used within the mining industry?
Okay, so what I'm going to do is then I'm actually going to share again, if you don't mind, because I'm going to go back to those two comparison images of the flood here. Okay, so with mining, we've all seen that there's what we refer to as mine dumps. Okay, so there's different types of mine dumps. So the one type is where it's just basically it's a rock that has been like dumped on the side. Okay, and those will be fairly stable. In the case of coal, if there's too much coal dust, they can be unbelievably dangerous, because what can happen is when you've got a coal dump and you've got not only coal dust and you've got sulfur dioxide, but also sometimes what happens is with rainfall, etc., you can start getting a little bit of rotting. You know, after all, it is actually, you know, coal used to be plant material. So you can start getting some methane, etc. So what can happen is that you can actually start getting some smoldering there, and it can actually start heating up inside, and then it becomes fluidized, and it can become very unstable. But the thing is that what we can see is there's actually quite a lot of precision in these photos. So what happens is that as the satellites pass over every 15 minutes, what they do is they take an image of those coal dumps, and then they can see what's happening temperature-wise. Are we actually getting some temperature rise? Because they would be able to detect that, because there may not be any smoke that we can see, from ground level. Also, the thing is there any slight movement? Because the thing is, unfortunately, when those break, then it's basically like a very, very fast lava flow that comes up, and they can be absolutely deadly and so incredibly destructive. And then you've got a third type of dump, which is actually, the technical name for it is actually called a slimes dam. So what that is that's very typical where you have got an extractive metallurgy, like for example, gold mining, silver mining, where you're digging up a lot of the ore and then you're crushing it very fine, and then you're dissolving the valuable, the gold or the silver, whatever it may be, from that solution. Then what happens is you get a slurry, and that is it's like a thick mud, and they call it a slime. This is an awful word, but so what it is, that your residue that then gets pumped out of the mine plant is this slurry or this slime. And then what that is done is then that is actually put into dams. And then what they do is over time it just builds up as it dries out, etc. But these things, as you can imagine, you've got this heap that is building of drying slurry and sludge over time, and those can also become unstable, and they can also break, and they can also, then you get this terrible mudslide. So that is, those are areas, and they do that by having similar images like this, high resolution images where they compare them. And then another example would be similar to that of the illegal fishing or the illegal boats, is that where we have illegal mining activities, that mining area should be completely closed off to people. But as humans, we can't help it. We're going to turn our phone on. We're going to do something, and so suddenly there's a ping from electromagnetic signal from somewhere, and there's not meant to be anybody there. So then they can identify that there's illegal mining. Okay, so Daniel is saying that he has a really bad network connection. Sorry about that, Daniel. Okay. Ramaloy, I've got here, how do your TGS incorporate to this EO? Sorry, why don't you just share with me what you're referring to as TGS? Hi. Sorry, you're muted.
Yeah, now can you hear me now?
Yeah, we can hear you.
When I'm talking TGS, I'm talking the tiny ground stations. You remember from our side, we are more into Earth observation and satellites after school learning clubs.
Yes.
Now we are trying to look into how do we incorporate establishing a TGS at our center with the bigger satellite observing with those satellites observing Africa at least 15 minutes per day. Every 15 minutes in a day.
Okay, great. Okay, so in terms of TGS, you're referring to the tiny ground station network. Okay, great. So what I'm going to do is I'm just going to share with everybody if you don't mind, I'm just going to go, I'm opening up my browser, And I'm going to go to the tinygs.org website, just so that we can get everybody onto the same page. Okay, so great. Let's go back to Zoom, and I'm going to share. So the tinygs ground station network. You can see here's a map of our. On this website. It's tinygs.com or tinygs.org, and really it's a community. And we can see over here there is over 8,000 individuals who participate. They've got over 2,000 ground stations, and this is the telemetry they receive. So these satellites that run on the tinygs ground station network are not necessarily those satellites that orbit every, that are able to scan our continent every 15 minutes. A lot of the Earth observation satellites, the majority of the Earth observation satellites that are in orbit, they have dedicated communication with their own ground stations. And the reason for that is that they don't necessarily want all of that data to be available from an open source perspective, because sometimes it can be really crucial in terms of national security. However, that being said, let me explain what the tinygs ground station network is all about. So all of these green dots over here are, in fact, ground stations. So what I'm going to do here is I'm going to zoom in, and what we can do is I find it quite difficult to navigate this map sometimes. What I'm going to do is I'm going to have a look at this one here. So this ground station here is called Nigeria Lagos. And it's so that is live at the moment. So what I'm going to do is I'm going to just zoom out now. You can see there's way too few tinygs ground stations on the African continent. There's a lot in Europe. There's a lot in North America. But what we can do is we can actually go down and we can have a look at. Let us take, for example, let me have a look here. Should be, let's have a look at this Oasis one. And if I actually have a look at this particular ground station, we can see that it's online, and we can also see that it is picking up satellite data across a very, very, very broad area. And
Judy, we have two of yours in the Cape.
So should I maybe what I should do is just search for those.
See if you can try, it's just search for Max IQ.
Stations. I'm going to go here.
It'll be Max IQ.
Bins. Okay, so what this does is this shows that's where your ground station is. Yeah. It's online. And so this is the area that it picks up in terms of how many satellites there are that it's picking up. So what it is it's an open source network where students who want to launch satellites and they don't want to necessarily want to build or have the budget to build their own dedicated ground station. What they will do is that they will use the tinygs network, because the thing is that what they will do is they will set up their own ground station, and then everybody else in that global community will assist them with downloading their packages. So it's very much, so that's why it's a community that is growing and growing and growing, because it means that as a student group, you only need to focus on your satellite build and launching your satellite, because you have this entire community that's going to help you with downloading. So what I'm going to do is that I'm going to actually start searching satellites now. And so what we want to do is we want to have a look at active satellites. And the one that's been in orbit for The longest is Norby. It's a Russian satellite. And then what we can do here is we can actually have a look. I'm sure that there's going to be one that does Earth observation. That's part of this network. Sorry, I'm going into this way too unprepared. So let's see if there's something that's got a multispectral satellite. Okay, this one looks like it'll have a multispectral satellite. So let's go here to Griffin 1. Okay, so we can see here, developed by a university. The satellite is a camera that captures images in 4 spectral bands with a resolution of 2.5 meters per pixel. That's actually quite good. So this Griffin, we can see now, where is Griffin? It is now in orbit. So it's been passing over the last number of orbits. It's been passing over South America. And then when it's on the other side of the world, it's been passing over Australia at night. So probably in a few hours, what it'll do is it'll pass a few times over the African continent. And then we can see here, let's have a look at this ground station. So here, go up. So here, this ground station has downloaded a packet from this particular satellite. And so that's pretty big. And so here it actually it shows us how many different satellites have been supported by this one particular ground station. But the ground stations usually are nothing like that size. They actually literally could fit into a shoebox. That is how incredibly small these I mean, Richard, your one is not much bigger than a shoebox, is it? When the antenna's folded in. So, Ramaloy, absolutely, we certainly could make sure that the tiny GS ground stations could support Earth observation satellites. What we could also do is we could also really encourage our local universities and technical colleges to build their own Earth observation satellites. We do have all of the components manufactured in South Africa. We could actually launch our own satellites made from our own hardware and certainly use that network. I hope I've answered your question sufficiently. So Daniel, you had, I'm actually going to, great. Daniel, you had this question. Are we truly utilizing the power of Earth observation in Africa, considering our current socioeconomic state? No, we're not. We could be doing a lot more in terms of Earth observation across the African continent. Our challenge for a lot of African countries right now is that they need to purchase their data from others. And usually they are either purchasing that data from US businesses or Canadian businesses. Sorry, not Canadian businesses as well as European businesses and the European Space Agency. So what it is that there's a cost associated with that. And not only that, it means that we don't actually have sovereignty over our own data. Those data feeds can be cut off at any time. So I know that there are some discussions with the African Space Agency to actually develop a constellation of satellites for the African Union that we could then launch. And so that as a continent, we could have sovereignty over our own data, our own Earth observation data. So the ideal number of satellites in a constellation so that you can get that 15-minute cadence, I think that is around, I think it's somewhere around 15 or 18 satellites in orbit. So if we farmed the work out to various companies across our continents, we would be able to do that ourselves. Unfortunately, right now we don't have our own launch capability on the continent. We used to have two launch sites, one off the coast of Kenya, and also one on the coast of Southern Africa. But unfortunately, those have been decommissioned some decades ago. So we wouldn't be able to launch it ourselves. We would have to procure a launch from one of the usual launch partners: Japan, China, India, US, Europe. They would then launch it for us. What we could do is we just go to private sector. The private sector will launch it. They're not particularly worried about where it comes from and who it belongs to, because they're private sector. And I know certainly with SES satellites, they don't have their own rockets to launch their own satellite fleet with, so they procure launchers, and it's just one of those things. It's fantastic. Very, very easy to do once we do that. And then Daniel's second question is, what do you think is the problem is? Lack of geospatial talents or lack of centralized geospatial database analysis and ready data? My feeling is what's holding us back is we don't actually have our own infrastructure, our own hardware in orbit. That is what I believe is actually holding us back. And if we actually take somebody quite close to me did some analysis some months back, and for what all of those countries are actually paying for their data, as well as the private sector, the entire mining industry is buying data from Europe. That constellation of Earth observation satellites would cost us less than we spend in 1 year as a continent buying data from others. So we actually should, if we just coordinate it, we should be able to do it. And and then what can we do as educators to contribute to innovation and the effective use of this technology? I know programs like this are a big move. Thank you very much, Daniel. That's wonderful. The thing is, at the moment, we actually do have access to the data. So as educators, just making youngsters aware that this data is available, that there are applications that they can explore. Because what it means is that with access to internet and Earth observation data, young people can actually build products and solutions and offerings from wherever they are. They don't need to move to a big city center to be able to do that. They could do that where they live. If they're in a rural area, if they're in a small village, in a small town, they could actually build and run a business from there. All they need is access to internet and access to Earth observation data. And please don't get me started on access to internet, because as far as I'm concerned, it actually should be a basic human right. And then that's it. I'm now done with the questions. Does anybody else have any questions? Caroline, I know you're always very engaged with these sessions. Dinesh as well, if you'd like to come in.
Hi, Judy. I don't have a question. I'm just excited and just looking forward to see how we can really have this in Kenya, because GPS, and it's actually going to be really good education for our students, especially for us after school STEM clubs. And it's really interesting to see how we're going to be able to combine the aspects of geography and STEM. Because I'm seeing a lot of geography. This is what we are also teaching our students here. So I'm no question, just happy to see the engagement and really happy with the Earth observation in Africa. It's really interesting, and wow, I just can't wait.
Great. Caroline, thank you very much. And congratulations. I know that last week you received an award. If you want to boast about that and tell everybody about your award, please.
Oh, yes. Okay, let me just have my camera on and then I just show you all the awards. So this is the award that I received. I don't know whether we can all see it.
Yes.
And so I'm so happy. It was great. It was a shock actually, because we were over 145 people, and they only had 35 nominees. And then we had only 10 honorees. Yeah, so happy to be among the 10 honorees under the STEM category. Yeah, and Missouri Awards 2026, my first award this year. I'm so happy because of the work we're doing in Kenya in STEM education. Thank you so
Great.
much.
Wonderful. And congratulations again, Caroline. That's absolutely fantastic. Excellent. Christelle, I can see you've been able to join us. Christelle is our champion from SES. And I was just wondering if you wanted to just say hello and greet everyone. And you're sorry you're muted.
Thank you so much, Judy. Now, certainly the session that you presented till now.
Oh, sorry, it's muted again somehow. Sorry, Christelle, you've muted again somehow. There we go.
Sorry for that. Yeah. Judy, thank you so much. The session up until now has been very informative. As I said, I've actually learned a few things. Although I'm from the satellite industry, working within the SES business, my focus is more on product strategy. And we don't always get into all of the use cases and, all of the applications of satellite technology. So thank you so much for that. And of course, we appreciate the work that you do across the continent so much, and glad to be here.
Great. Yes, thank you so much. I agree with you. Sometimes we're so deep in our topic that we don't realize actually what an impact that we could be having, that we maybe are having, that we're not aware of. And also sometimes it just needs to be explained by somebody from the outside.
Of course. And what we spoke about today is really Earth observation, but when you look at all of the other applications, my speciality is really media distribution, which is a whole different game. So
yes, yeah, absolutely. Christelle, actually, it would be quite great if you could share quite a lot of that field with us, because my stance is very much, I'm a scientist and a chemist. So I'm always going to look at that. Does it involve water or gases or whatever it is? But it would be really great. Let's take it offline, and maybe, there's a lot of youngsters across our continent who really want to understand the media and communications industries, and what are the career opportunities for them that doesn't involve water.
Yes, no, definitely. It certainly it widens the scope so much.
Yeah, that would be great. Thank you. Thank you so much, and also thank you so much for the support for the program. Danish, I was wondering, Danish has actually been a friend of the Space STEM program for multiple years. Danish, I'm not sure if you want to come in with some comments.
Yeah, thank you very much for the session. That was so wonderful. And thanks for everyone for sharing. Congratulations, Caroline. Yeah, I'm so much glad that we've been working together on this program, and our students are really, really enjoying. They've been using those gadgets that we donated for this. And like we said, we are working on establishing or maybe starting our TGS this year. So thank you very much for this, for the guidance. And for the session, I did geography in high school, and when you are sharing this about the Earth observation is reminding me a lot, and really giving me like to see the practical application of maybe what we learned. So thank you very much, and we hope to do more for the continent of Africa. Yeah, thank you.
Great. Dinesh, yes, you are correct. When we sent out the hardware last year, we did include tiny GS ground station kits. So yes, one of our next projects is to get to connect those and start running those tiny GS ground stations. I'm not sure if there's any more questions before we wrap. Great. Once again, thank you everybody for joining for this workshop. And I'm looking forward to being able to let everybody know that, in terms of the future topics that we have going forward. And finally, thank you to all of you as educators and facilitators, because what you are doing is you're changing the lives of hundreds, thousands of youngsters making sure that they have fantastic futures. Great. And for now, that's from me, Judy, over and out. Cheers.
Thank you.
Thanks. Cheers.
Bye. Bye.
Bye-bye. Thank you.
Thanks. Cheers.